here. So this will be a short introduction to section 6. If you guys recall from our schedule, we went out of sequence from most textbooks. We covered the first several chapters on structure, bonding, arrow pushing, stereochemistry, conformations, and then we went out of sequence to the middle of the textbook and we learned about spectroscopy. And I don't know about you guys from your perspective, but from my side of the table, it just makes so much more sense. I introduced functional groups to you, and then I tested you on how spectroscopy uses functional groups. Talked to you about different conformations and energies, and then we talked about how light can interact with different things. So it just, I don't know, it feels like a good a good platform for building the rest of the semester, which is how do molecules behave? How do we analyze them? What are all the different terms we need to know to understand molecules? The second half of our semester is all about reactions in organic chemistry. Section 6, we're going to spend maybe 10 minutes and maybe tomorrow's class just understanding different types of reactions, terms that show up, reviewing, just getting an overview of stuff. Then we're going to come back and really dive into these reactions. We'll look at alkenes. We're going to come back to nomenclature and reinforce how to name alkenes. We're going to look at alkynes and do nomenclature again, and alcohols and alkyl halides, just review of nomenclature throughout the rest of the semester, with kind of challenging a little bit more with different functional groups. We're going to learn what reactions alkenes can go through. We're going to learn how to make alkenes. We're going to see the same in alkynes, alkyl halides, and alcohols. So by the end of the semester, we're going to have under our belts about 20 to 30 different reactions. Kind of depends on how you group and classify them. And so with this section 6, just an overview of organic reactions, I just want to paint the big picture for you. What are the terms we use? What will you have to expect? How do you read an organic reaction? Yeah. So let's start here. If we were to write a generic organic reaction, and by that I mean I'm not going to put a molecule in here, I'm just going to put words. Some people will say that the starting material is referred to as a substrate. This is what you want to do a reaction on. In general chemistry, you typically say A plus B plus C goes to form D plus E plus F. But in organic chemistry, I'm not sure why they do this. They kind of like to condense it a little bit more. So they highlight the main substrate of the reaction, and then over the reaction arrow, they're going to put reagents. Sometimes these reagents are organic. Like, I'll take bromocyclohexane and I'll react with methanol. Organic substrate, organic reagent. Why isn't methanol the substrate? Doesn't really matter. Sometimes reagent and substrate can be swapped, substituted with each other. It's more about just like, what is your focus? What are you trying to start from? Sometimes a reagent is inorganic, like Br2, Cl2. Sometimes the reagent is a catalyst. And oftentimes catalysts are inorganic. For instance, iron 3 bromide is a catalyst we use in reactions with aromatic rings. Or hydronium, H3O+, is an inorganic catalyst that we use for hydration reactions. So reagents can be organic or inorganic. Oftentimes underneath the reaction arrow, but not always, we'll put solvents. Our solvents are often put into 3 categories: polar protic, something that has a dipole moment. And what does protic mean? Yeah, a donatable hydrogen. It's acidic. Protic, proton acid. So a good polar protic solvent is something like water, methanol, ethanol, isopropyl alcohol. All very good polar protic solvents. Even acetic acid, vinegar, can be used as a polar protic solvent. So maybe I'll give you guys those examples: H2O, ROH, and acetic acid. Polar aprotic, something that is polar but can't donate a hydrogen. There's several very common reagents here. Ether is very common. One of the most common ethers is THF, tetrahydrofuran. It's a 5-membered ring that contains an oxygen. Also diethyl ether, if you guys have been in lab. And diethyl ether can be written a couple of different ways. Draw its Lewis structure, or its bond line structure, or its condensed molecular formula, diethyl ether, Et2O. Another common inexpensive reagent, other than ether, is acetone. Acetone is not acidic, but it's very polar. And then depending on what realm you might work in, I know Brett will like this one, DMSO is another very common polar aprotic solvent. DMSO is a dimethyl sulfoxide. So it's got 2 methyl groups connected to this sulfur-oxygen double bond. Nonpolar solvents, quite honestly, are less common. But here you might see something like hexanes being used. You might see toluene being used. You might see benzene. Toluene is an aromatic ring that has a methyl group coming off of it. No electronegative atoms, nothing like that. Now, it's very common for you to see reagents on top and solvent on bottom, but it is not mandated. You can see reagents and solvents written across the top. You can see those flipped. And because there's no systematic rule, you can see any of these flipped really anywhere you want to. Notice also how some of the, many of the solvents are also organic solvents. Or organic molecules, I should say. So that sometimes you have a substrate, a reagent, and a solvent, all organic. Oftentimes, the organic solvents do act as reagents. And when a solvent performs a reaction, we call it solvolysis. Kind of reminds me of electrolysis in your Gen Chem days, where you make electricity perform a reaction. Solvolysis is when your solvent runs a reaction. We'll look at reactions that are solvolysis. What goes on the right-hand side? Products. I'm going to put this in parentheses because sometimes our reactions will give us different structural isomers. Sometimes our reactions will give us different stereoisomers. Sometimes our reactions really only give us one product. Sometimes we get a major product. It's the most stable, it's the easiest to form, and so it is produced at 80% yield, but we also get a minor product. We get something that's only produced at 10% of the yield, or in other words, it becomes an impurity in the desired product because there's different pathways that these reactions can go through. We're going to look at different types of reactions. We're going to look at different classifications. But throughout these next 2 units, with alkenes, with alkynes, with alkyl halides, with alcohols, what you'll be tested on with reactions is, given the reagents and the products, can you tell me what starting material is needed? Or what starting material does not work out of a multiple choice question? Or given the substrate and the products, can you figure out what reagents are necessary to transform the starting material into the product? Basically, analyze what functional groups you start with, what functional groups you end up with, and find the reagents that perform that transformation. And then, of course, you'll need to be able to tell me, given the starting material and the reagents, what is the expected product? What functional group, what structural isomer, what stereoisomers do we expect from it? So just to give you a heads up, the unit test here for Unit 4, your multiple choice questions, I've got one bank of questions that says reaction product. So you're given 1 and 2, you have to predict 3. Reaction reagent, you're given 1 and 3, you need to fill in 2. Reaction starting material, you have 2 and 3, you need to find 1. We're going to talk more about how these reactions often take place in multiple steps, and that creates intermediates. You guys will need to be able to predict intermediates that form as well. And we're going to be learning how to do a mechanism, which is how can we predict what bonds break, what bonds form, in what order? How many individual steps are needed to get to the final product? You don't walk into a doctor's office and leave with a cast. First, they have to roll up your sleeve. Then they have to wrap it with plaster. Then they have to add the external layer. There's multiple steps. It's not just one step. It's very similar with mechanisms. Things have to happen in specific sequences in order for a total reaction to take place. All right? We'll talk more about organic reactions tomorrow, and then we're going to see a ton of them next week. Okay, have a good day.